Good morning. Today is October 28th, 2017, and this is the John Chappell Natural Philosophy Society Saturday Science Chat. And this week we have Mohano Habib again this week. And last week we had discussed the rotation of the moon. So you have two other videos that you had presented, one on gravity and one on the ether. So I'm going to let you take it away. And what would you like to discuss? Just a second, I got to unmute you. Okay. All right, go ahead.
I think we will start with gravity first.
All right, gravity. So let's see here. Do you want me to start the video, or can you just, why don't you give an introduction to that while I find that video?
See, basically, mass and weight are defined as two different characteristics of matter. So mass is defined as the amount of stuff in an object, and weight is defined as the force of gravity acting on that object. So we believe this to be true because from our childhood and from almost 300 years, this is being taught to us. Now, during free fall, there is a gravity-free environment. If you observe the floor of the elevator, when it is falling down at an acceleration of 9.81 meters per second, the objects resting on the floor of the elevator, like a person standing in the elevator, or an object which is resting on the floor of the elevator, it will feel no gravitational force during free fall. So in that time, if you find out its weight is equal to mass into acceleration. Now acceleration is 0 during free fall. So weight is equal to mass into acceleration. So weight is equal to 0 newtons. So my question is, will since the weight is 0 newtons, can we easily lift up that object during free fall? Or will we have to put effort like we put on the Earth's surface? Normally when we lift up a heavy object, we have to put a lot of force, apply a lot of force. During free fall, to lift up that object, do we have to again put force, or will the object come up very easily? This is my doubt and this is my question.
All right, well, I think I've queued up that part of the video here. So we're looking at your YouTube video on gravity. It's entitled Gravity 27, May 2017. And this is going to play at around 3 minutes, 50 seconds. And this is the one with the elevator, your elevator video. We can show that. So let me go ahead and share that. Okay. Gonna have. I don't think there's any significant video. You can go ahead and There's a
very tall building inside which a person and an object of mass 200 kg are resting on two different weighing scales. If the elevator's cables were to snap suddenly, it, along with everything inside it, will go into a free fall, due to which the weight indicated on both the scales will be 0. If gravity is really present, then the person should be able to lift up the 200 kg object effortlessly. However, if he has to apply force to lift up the object, then it is explicitly clear that such a force does not exist. Since this experiment is dangerous and can be performed only by an expert stuntman, we can adopt the experiment illustrated in the video. We need a hollow contraption, as illustrated in the video, weighing scale, iron block of 250 grams, and electromagnet, along with necessary batteries and fiber. A video camera fitted inside the contraption would be an added benefit. The distance between the electromagnet and the object should be adjusted such that when it is switched on, it should be capable of lifting up an object of at least 150 grams. The contraption must be dropped from a considerable height with the timer set to switch on in 1 or 2 seconds after free fall has begun. If the weight of the object really becomes zero, then the electromagnets and traction will pull up the object, which will then attach itself to it. However, if the object retains its weight, then it will continue to remain resting on the weighing scale even after free fall is completed. In the experiments I conducted, the object was always resting on the weighing scale during and after free fall, proving beyond doubt that a gravitational force does not exist and that weight is an inherent property of matter and not a property endowed by gravity. Some videos posted by reputed space agencies show similar experiments where an object hanging from a tension spring immediately appears to rise up when the contraption is dropped, giving the impression that the object's weight has really become zero. However, what is really happening here is that when the contraption is dropped, the downward motion is not immediately transferred to the object. It remains stationary, as in the case of a slinky spring, until the spring closes completely due to the descent of the contraption and will only then begin to fall along with it. In the
Okay.
May I ask the question? Maybe one question, so just to clear up some uncertainty. So, does the presenter? How you pronounce your name? Sorry. Am I heard?
Yeah, we're hearing you.
So, just wanted to ask, I mean, does the presenter assume that the person would not need to put any effort to lift that weight in the elevator while elevator is falling down?
Do you hear the question?
No, I didn't get it clearly. Yeah, can you please repeat?
Yeah. Do you assume that the person is not supposed to put any effort in lifting up that weight in the elevator why elevator is falling down, right?
Yeah.
Actually, I wanted to suggest, actually, I mean, to think along the line about a clear distinction between, say, static situation and dynamic situation. Actually, what is the weight? It is actually the situation when dynamics, gets into statics. You know, so always actually when you, for example, if the bodies are falling, I mean, the falling body doctrine of Aristotle, right, which is still in power in my view because of centrality of mass in the physics in general. So it was not true, right? So because bodies of the different weights are falling with same velocity, same acceleration, but once they got hooked on some dynamometer or a spring, then they will extend those springs to the amount of the mass. And mass is actually kind of statical measure of quantity of matter. And dynamically, there is no any influence of quantity of matter. Apparently, everything goes on the level of atoms or whatever. So here, I mean, although those bodies are falling with the same acceleration, that doesn't mean if you are going to change the place, put some velocity acceleration on it, that you are not supposed to invest the energy force. So, in my view, the person would need to put effort from the point of starting to lift that weight to the point when that weight gets certain height. From that point on, the person is not supposed to feel any stress, any effort while holding that. But while lifting, it has to.
Correct. So then what is the purpose of gravity? If by lifting you have to apply force, the gravitational force is not acting during free fall. It is zero.
No,
So
no,
then what is the function of gravity?
it's not acting. It's not acting. How say if you don't change, how say that static situation. But once you start changing the static situation, the investment of force or energy work should be needed. I mean, we can look later on the spring, you know. For example, that spring that is taking place of the magnets. Actually, what takes, we have a situation actually that the weight doesn't, how say, fall until all the potential energy of the spring is exhausted. Because, you know, it will be holding on it. Once that exhausts, then the weight will start proceeding, kind of falling in concert with all other bodies around. So we will, I mean, I understand your kind of, how say, motivation and everything is very important, really, and interesting. But I think we could come up with a pretty good resolution of whatever might be looking unresolved.
No, I want to make my point clear once again.
So
See, the
I wanted to suggest to strictly distinguish between static and dynamic situation.
no, sir, I
As long as we have static situation, we have, you know, when we have the dynamic situation, bodies are falling with the same rate or rate of change of speed. And, you know, if we are holding something in hand, we will not feel the strain of holding that body.
Correct.
But but if you would like to lift that body while you are holding it and falling together with it, you will feel a stress. You would need to invest energy
Correct.
to do work to lift it, because you actually acting against the pressure there. I mean, of course, if you get into aerodynamics, then gravity becomes as a pressure gradient. And you know, actually, when we have that in mind, for example, then it will be clear that once we acting against certain pressure in the medium, they are supposed to invest force. Okay, anyway, I mean, just maybe it would be too much, but for beginning. But I suggest to clearly differentiate between static and dynamic force, and whatever we change, how say, between these two statuses, how say, between these two, how say, situations, right? Then we have to consider investing work being done or dissipated or whatever.
No, here the important thing is during free fall, weight. See, when an object is resting on the Earth's surface, its weight is equal to mass into acceleration due to gravity. But the uniqueness of this experiment is the floor of the elevator, which is in free fall, is equivalent to a body, celestial body, where gravity is zero.
Yeah, okay. I mean, what does it mean gravity is zero?
So
Gravity is not zero. Okay. So, sorry, excuse me. You cannot say that gravity is zero.
No, gravity zero means the gravity acting on the object which is in free fall. Which
I mean,
is resting on the
if you identify gravity with weight, then you would say gravity is zero. But no, gravity is not zero. But the static effect of gravity is zero while falling. Free fall means that any static effect of gravity is nil, is non-existent. But once you change the situation, put some hook for that body on spring to be caught on, you will see gravity in terms of weight. But the biggest mistake, biggest confusion in physics in general is kind of confusing weight and gravity. And weight as force of gravity, statical aspects of force of gravity.
Okay, I will ask
with
this
dynamics
question.
And so on and so on and so on.
Yeah, I will ask this question in another way. Now, suppose we are standing on the Earth. gravity is there. That is why we are feeling the weight, we say. Suppose just let us presume that gravity is vanished, that
Yes.
for a few moments there is no gravity. What will happen to us? Will we float, or we can lift up any object just like that?
We will be just falling down. I mean, to the extent that kind of we are going
No, I
attracted
think
to
the
the
answer is
center.
yes. The answer clearly should be yes. Let's just go with that answer.
Yes.
You should be able to easily lift up the object if there was no gravity.
Correct. That same thing is happening on the elevator floor. The uniqueness of the falling elevator is its floor during free fall, objects resting on the floor of a elevator which is in free fall are experiencing zero gravitational force because
You
they are
cannot say
falling.
that. Sorry, excuse me. You
No,
cannot
no,
say
no,
that. You cannot say that. I mean, say,
no,
you
that is
can
what
say you can say okay. You can say that you don't feel pressure on your feet, for example, or
no.
if you are holding something, you're not going to feel its weight. But once you try to change the relative position between you and that weight, you will see the effect of gravity. You know,
No.
because
What I meant
once
to
you just
say,
is the dynamic situation, nobody, how say, no taking, there is no place for Aristotle's falling body doctrine, of course, as Galileo finally showed after some priests that were dropping some stuff from those towers and anyway. So that's fine. But once you change that, once you put some hook and those bodies or you got on it, you will see then the gravity force in the form of weight. But the force is always there.
yeah,
That
force
pressure
is, I am not
gradient
denying
is
that.
always there.
See, I am not denying that force is there, but since you are falling at the exact same rate of acceleration as the gravity, you will not feel the force. That is what I am telling. I am not telling that
Yes, yes,
gravity has
yes.
vanished.
But if you do anything that change the relative position of bodies, if you change the relative position of that weight that is sitting on the floor of the elevator, at that very moment you will feel the weight.
Yeah, but why we should feel? That is what I am asking. You should not feel the weight because there is no force acting on it during free fall. It is
No,
equal to.
you would feel that weight if you start to lift that weight.
Correct. You feel, that means there is no gravity. No, if there is gravity, then it is not acting during free fall. So
No,
weight.
it is acting. If there would not be gravity, you would not be free falling, and nothing
No,
would be free falling if there would not gravity. So there is gravity. There is dynamic effects of gravity. But if you put some hurdle, try to stop it or try to change direction, to lift it up, counter of that force, of that effect, then you will feel you would have to invest the fork.
I agree with you that we have to apply force, but why should we apply force? Because theoretically speaking, during free fall, the weight of the object is zero. W is equal
But
to
you are confusing. Excuse me. You are confusing.
No.
Then you're confusing the gravity as weight and gravity as dynamic effect. Weight is gravity in static situation. It's very simple.
No, during free fall, it is very obvious that the force of gravity acting on the object resting on the floor of an elevator is zero because it is falling along with it. That is why the weighing scale also shows zero.
Yes,
Right?
okay, I agree with that.
So that means in terms of newtons, when you say weight, in terms of newtons, mass into acceleration is zero. Because it is falling exactly like that. We will neglect
So
friction.
a relative acceleration of you and that weight is zero. I agree.
Yeah. So when that means the answer you will get W is equal to m into 0 is equal to weight is equal to 0 newtons. The same thing will happen.
Can I try and clarify? I want to clarify because I've reviewed the video here, and I mean what you're predicting is very different than what most people think would happen.
And that is the problem.
Right? So let me have an illustration here. Let me see if I get this right. Okay. Now let's pretend this is a very, very heavy object. Let's pretend this is made out of lead. If this is made out of lead, you know, it's going to fall on my desk.
Which minute is that? If you are watching some movie?
No, we're not watching a movie. We're just looking at I just got my garbage can. We're pretending it's made out of lead. Okay. Now, there is no way that I would be able to lift this bucket on the planet Earth, right? Now,
correct.
What you're saying that is if suddenly my whole house started dropping in free fall, then I would still not be able to lift this thing up. Is that correct?
No, contrary. He thinks you would not put.
Please not interrupt. I'm asking the speaker. I want to clarify. So if my house was falling, then I would still not be able to lift this up. Is that correct?
No. If gravity is there, see, the first part of your question I will tell. Now you kept the lead on the table and you have to apply effort. Why we have to apply effort? Because the force of gravity is acting on that object, right?
Yes, that's right.
We cannot lift it because the force of gravity is acting on the object and the object is resting on the table or floor or whatever. So that is why we cannot lift up, because the gravitational force is acting on it. So when you free fall, that is exactly along with the gravitational force you are falling, then the gravitational force acting on that object, lead object, will become zero.
How do I join in, please?
Yeah. So, which means that if you have the effort again, the same effort as before, then that means there is no gravity. Because, okay, I will try to put it in another way. Okay, we have kept the lead object on the table. Now, forget the house falling. Think gravity has disappeared for a few seconds. Gravity has vanished. It is just a presumption. Then, will we be able to lift up that object or not? That is my question.
Well, what is your answer? That's what I'm trying to find out. What is your answer? Will I be able to lift it up or not?
No. See, now let us forget about free fall.
Now, can you please just answer my question? I'm asking you a very simple question. In your theory, will I be able to lift this up or not while my house is in free fall? The only answer I'll accept is yes or no.
Okay. As per theory, you should be able to lift up.
I want to hear just yes or no.
As per theory, no. You should not.
No, I will not be able to lift this up, even when my house is free falling.
No, that's what. As per theory, you should be able to lift up. As per practically, you will not be able to lift up, which means only one thing: the gravity does not exist.
Okay. So, just to make this clear, because I don't want to confuse mainstream theory and what you're predicting. You're predicting that even if my house goes into free fall, I will not be able to lift this thing up.
No, he says...
Because theoretically you should be able to lift up, but
no,
you cannot lift it.
I don't want theory. I want to know what you're predicting.
My prediction is you will not be able to lift up even in free fall. That is what I predict.
I will not be able to lift this up. Okay.
Yes, correct. Then what is the function of gravity? You tell me. Where is gravity then? What is the need of gravity?
Can I come in here?
Sure. Let's have someone else talk.
Right. Okay. I would say that if the lift is in free fall, you would find that the lead weight has weight, because in lifting it up, you are changing its speed in falling. So there's a difference in you falling and that falling. Also, there seems to be a confusion. Surely you can't have free fall without gravity, because you're falling towards gravity. The fact that you feel weight less is because you are falling towards gravity, and that equals out gravity. But in fact, if there's no gravity, there's nothing to free fall towards.
Now, if I were to represent mainstream, I would say that this experiment has been done in orbiting spacecraft, because orbiting spacecraft are actually in free fall, just like the elevator.
No,
Because
there,
all they're doing is that they're escaping hitting the ground, because they are just going around the curvature of the Earth. So a mainstream scientist, and I'm just being a devil's advocate here, would say that we know that when the astronauts are in fact in their orbital path, and they are in fact within like 98% of the strength of gravity while they're in orbit, that when they have gigantic lead objects like this, yes, they can just go and move it with the finger like that very easily. So that would
Horizontally, maybe not vertically.
No, vertically, horizontally, any direction you want. They can move
horizontally
very, very heavy objects while they're in the spacecraft. And basically, they only have to overcome the inertial force. But if this was like a 1,000-pound object, they could move that with the finger. They could move a 1,000-pound object with a finger up in space. So that would show that that's
another thing. Actually, that means actually that the gravitational acceleration is small, is low, much lower than on the close to the Earth's surface. That's the difference.
Well, there's two different forces here. There's the force of gravity, which on the Earth is very, very strong. Like if this is 1,000 pounds,
that's a big difference.
And then there's the inertial force, which is proportional. But if I put this 1,000-pound lead brick on a air cushion, then I could still just easily push it with my finger, with just a few newtons worth of force.
We have been talking about lift, about elevators, and elevators we have still only on Earth, right? So please consider a situation when we have strong. So I don't see. I mean, I was talking all the time. I mean, suggesting that the effort should be put to lift that weight. And I had the impression that presenter was talking different thing. And later, after you, Franklin, was sitting on a clear answer, yes or no, that it turned out that both I and him, and maybe all others, are in agreement, right?
No, I don't.
Is there anybody here who would say that there would not be need to put any effort to lift that weight in the falling elevator? For example, for half meter or 1 meter from the floor of elevator. Is anybody who say yes or no?
There's a slight weight.
No need for force. Need for force.
There's a slight weight because you are changing its falling speed. So
we all agree. The situation would be same as on the Earth, almost. Assuming that the gravity acceleration is the same. For example, the lift is on the height of 10 meters, for example, right? And on the 5th meter, we start lifting, right? It will be very similar as lifting it on the Earth's surface. Do we all agree with that?
No, I think we would all disagree with that.
You say, okay. Franklin, do we all agree or disagree? Who agrees that one has to put effort? Who says no? Please, yes, no.
It's not a matter of...
Please, yes, no. Please.
What is your specific question?
Okay. Now, yeah. What you asking me now? I mean, so all the time we're talking about this, right? So, okay. My question. Okay, you are falling in the elevator to get the elevator, and with that weight of 50 kilograms, for example, you start falling from 10 meters height, and then on 5th meter you start lifting it, assuming that the gravitational accelerator is the same on that level of height of 5 meters as on the Earth's surface. Would you be supposed to put effort to lift that weight for, say, half meter?
No.
To lift it from the floor? Yeah, I say yes. You say no. Who say yes? Who say no? Please.
Yes, I say yes.
2 yes, 1 no. Please continue. How many people we have here?
Bill, what do you say?
Bill, yes, no. Franklin, please rephrase question and situation because, I may not be well...
situation is this. I have 1,000-pound weight. My house is falling. We dropped it from 3,000 feet. The question is, can I lift this up like this? Or is it going to be like this? I can't lift it up. It's still too heavy.
Yeah, it's pretty heavy. So pretty heavy. So,
You think
for
it's still
whom,
pretty heavy?
for whom it will be still heavy, for whom not?
No.
Okay, you presenter say no, right?
No, the presenter
So
says yes. The presenter
yes,
says,
yes,
well,
I say yes. 2 yes, 1 no.
the presenter says
Two
this
is-
is heavy.
2 yes, 1 no. Please continue. How many people we have here?
My opinion is that you can easily start lifting it, but accelerating is depending on the mass.
So 3 yes, yes.
Of the
3 yes,
object.
okay.
So you
Okay.
can accelerate it, but the relative motion can be put without nearly any
Okay.
work. It is easy. So
3 yes, 1 no.
Franklin can easily lift it up.
So you
3 yes, 1 no. 3 yes, 1 no.
On
Okay.
his house.
I mean, slow it down. I don't want to confuse this issue about inertial.
No. 3 yes, 1 no. How many people we have here? Frankly, please.
No,
Cooperate.
see,
Please
Hans,
cooperate.
no, I'm the
3
moderator.
people say yes,
I'm the
3 people say yes, 1 say no. Please continue.
I'm the moderator.
Bill, are you there?
You're confusing the inertial mass
No.
acceleration.
I'm not stupid. I'm not confusing it. If we would be too far, very far away from any mass, then we would be able to talk only about inertial. We here are talking about gravitation, right? You put 3,000 feet. Put it 100 feet. Put it 10 feet. Put it centimeter, millimeter. Please don't confuse. Are we going, eliminating, notwithstanding inertial situation? I mean, there is no gravity at all. In the gravity field, are we going to feel any effort if we change the status of the falling body, which is next to us, in the opposite direction? I think we had 3 yes and 1 no.
Well, Hans was agreeing with me, so that would be actually...
No, Hans is agreeing with me. No, Franklin. Please, Hans, say, is your answer yes or no?
Where's this taking us?
I was
Yes, right?
stating that
Yes or no? Yes or no, please.
Franklin can easily lift his heavy weight.
That would be a no.
Say yes, no, right? What you mean easily? What you mean easily? If he is 10,000 miles up, yes, it will be pretty easy, right? But if it is just 1 centimeter, 10 meters, 1 meter, 30 meters, 100 meters, would it be easy?
If it is in free fall, it doesn't matter. He can easily lift it up. With respect,
So yes, I know. Okay. 2 yes, 2 no. Okay. 2 yes, 2 no. Please continue.
That is with respect to the house that is traveling with him.
Yes.
Just to make
Okay,
sure...
Franklin, take over, please. Take over. I give up. Take over. Sorry,
I
thank you.
just want to make sure your point is clear. That you still think that I would be unable to lift this object off the table if I was free falling from some 10 meters, right? So if you're thinking
Yes.
I would still not be able to lift this up.
Yes. And
So
then, to my surprise, also presenter says so. Yes.
Yes. Okay. Well, that is completely opposite of what the mainstream would say. The mainstream would say that as soon as I go into free fall at any point, I should be able to just go, whoop. That's 1,000
Yes,
pounds.
yes.
Doesn't matter. Doesn't matter. 1,000 pounds, go like that.
Correct.
Easily.
That's why the mainstream is in situation in which it is.
All right. Well, you agree with the speaker, so the speaker could be very happy about that. Right? You've got us in order. But let's say, so what does say Jim or Bill have to say about that? What say you guys?
Well, if you had been on a satellite or a rocket around the Earth, you would discover that it takes a force to move an object. It may be floating in your space capsule, But when you try to accelerate it, you have to provide a force.
Yeah, but that's a very small inertial force. I think a lot of this whole discussion, people can.
Why don't you eliminate, Franklin, inertial force, inertial situation, please, in the inertial force, please? Why don't you neglect that? You know, abstract it. Please remove it from consideration for this situation, right?
Yes, it's such a small force anyways. I mean, it's clearly much, much less than gravity. So let's not consider the force required to move an object inertially, right? So that we eliminate that confusion. But Bill, so what do you think of the discussion? So would I be able to lift my 1,000-pound weight off my desk if my house is free falling easily without any neglecting the inertial force required? Or would it still be under the full force of gravity, as the speaker asserts?
Well, if you go back to the experience that our astronauts are having, it takes a force to move it. Not as big a force as on the Earth, but it still takes a force, and the force diminishes as you get higher and higher above the surface of the Earth.
So 3-2.
So you're and the force of inertia is due to the effect of gravity. In other words, gravity.
No. Okay. Bill, please reconsider. Okay, first of all, we neglected inertial stuff, and inertial stuff totally different thing, right? So inertial thing is where we don't have gravity at all, right?
No, gravity. The force of inertia is due to the gravity of the non-local parts of the universe on that object, and what we call the force of gravity is the local effect. All the distant stars, the force of gravity is causing the force of inertia.
Okay, we Franklin clearly asked to neglect, to eliminate the inertial aspect, right?
Well, let's say for my 1,000-pound weight, that if we happen to find a spot where there's, like, between the Earth and the Moon, which is 0 gravity point, you can find some point there where the effects of gravity are completely nulled out. It will take just 1 pound of force to accelerate this 1,000-pound weight to, say, 10 miles per hour. Versus when this 1,000-pound weight is sitting on the Earth, it takes 1,000 pounds worth of force to move it up against the force of gravity. So there's a difference between 1 pound and 1,000 pounds. Okay? Now, what the speaker is saying is that even in free fall, in order to move that weight, we'd still have to exert 1,000 pounds worth of force to move it up against the force of gravity, even if we're in free fall. Versus what mainstream would say is that, no, in free fall, you would only need to exert that 1 pound of force in order to accelerate it, the 10 meters per second, or 1 meter per second, to get it going. So that's a big difference, okay? And
I really would not like to know if mainstream really holds that like that, Franklin, Bill, is it really so?
Well, like I said, the experimental evidence from people who are orbiting in spacecraft shows that, yeah, they can push 1,000-pound object with their
No. I mean, okay. We are talking about low elevation, right? I mean, completely. Okay, man. What mainstream general theory of relativity would say for such situation?
I mean, although the speaker has
this is the situation where general theory of relativity started, right? The Einstein's kind of revelation, right? Right? To equate gravity with the acceleration, right? So, what would Einstein say, or maybe people after him? Would that weight be just effortlessly be able to lift, or no?
Well, I would say even the speaker's video, which shows the scale weight goes to 0 in free fall. Now, basically, the scale is basically just telling you how much
force
is being exerted, or how much force it would take to move the object. And by it going to 0, that is indicating that it wouldn't take any force to move the object.
No. Okay. No, please don't confuse. Don't confuse the situation. I mean, what scales indicates is okay. I mean, right? That would be the same as on Earth. You would lift that weight from the scale, right? But the question here is, if that instead of scale, you have the spring, right?
Well, the scale is exactly reflecting the amount of force that you would have to exert yourself to lift up the object. Would you agree?
Yes. But
so if you agree the scale is showing the same amount of force that a person would have to exert in lifting
no,
the object.
that's the situation when person was not evolved at all, right? So please replace the scale with the spring, and then that spring is attached to the weight and to the bottom to the floor of the lift. Now you are lifting that weight. Or, I mean, okay, maybe I'm not sure if I can, but are you going to invest some effort there or not? I think we had three answers yes and the two answers no. I mean, I'm not going to take your role here. I mean,
we're not looking at all the parts of the problem. If we're doing vertical falling and you try to move the weight sideways,
don't be talking up, Bill.
Force a significant.
Let him speak.
To defeat.
Let him speak.
And so it's a three-dimensional problem, and we're only looking at one dimension. And I think if you just look at one dimension, you don't see the full issues. And so the mass of the particle or of the object is not decreasing because it's falling. And still, if you want to move it to the side, it will take a force to do that. And
a small force.
The faster you want to move it, the more force it's going to take.
Why not talking only vertically? I mean, why now this squeezing?
It's unreal to just look at one dimension. You have to.
How come it's unreal? You are sitting in the lift and lifting that weight. How come it's not that real?
Because if you weigh how much force it takes to move it to the side, you'll see the force is not zero.
No, I mean, okay, why talking side? Going up, look at your muscles. Are your muscles going to be putting effort to lift that weight vertically or not? Yes, so we have 3 yes and 2 no, right?
You have it on a scale and you rise it up, it will have a weight.
Oh, great, thank you. So 3 to 1, right? Frank, please. Catch on.
So, Bill, the question is, if this is a 1,000-pound weight on my desk that I can't possibly lift up, right? And my house is in Freefall, will you predict that I should be able to just go, oh, it's Freefall, I can lift it up? Or that's case A, or case B, during Freefall, I will not be able to lift this up still. So is it A or B?
If you tried to lift it up fast enough to lower your velocity to 0, you would have the full weight.
What answer does that mean? I just gave you 2 choices. It's either I cannot lift it up. I mean, this is a very stark difference. Either I cannot lift it up, or B, I can lift it up. During Freefall, what will it be? Will my weight still be stuck to the desk during Freefall, or will I be able to easily lift it away? Only overcoming the inertial acceleration.
If I'm in an elevator and I'm starting to fall, I can lift. It takes a lot of force to initially lift it up, but as I fall faster, it takes less force.
Well, that's a hybrid answer. So you're saying that initially we go directly into Freefall. I still won't be able to lift this up until we accelerate to, like, say, 100 miles an hour. Then I'll be able to lift it up. Is that what you're saying?
Yeah. Have you ever been in an elevator?
Well, I'm talking about something that will accelerate
on a scale to see your weight. You would see a lot of these effects on the scale. And you're assuming
I'm surprised
that
I can't get a
zero.
straight answer out of anybody here. So,
if you tried to jump while you were on the elevator falling, you try to jump off the floor, you will see that it takes force to do that.
now, to me, this doesn't make any sense. So let's suppose I go to let's go to a 100-story building here, okay? And I grab onto my 1,000-pound weight. Now, if I jump off the 1,000-story building in free fall, I'm pretty sure that I can go like this all day long, and it wouldn't make any difference. Whereas the speaker is saying that no, I would still not be able to lift and move that weight. It would be stuck to like if I jumped off with my table.
If your house,
let's get rid of the house. I'm just jumping out the window with my table and my 1,000-pound weight. And the speaker is saying that no, the weight would remain glued to the table. I would not be able to lift it. That is what the speaker is saying. That's what the speaker is saying, right? The speaker is saying is that I would not be able to lift this off after I jumped off the building with my table and my 1,000-pound weight, right? That's what the speaker is saying.
Freefall would be the same as if you were in a rocket ship or in the ISS. You'd be able to move it easily. I
should be able to, that's what I say. I think we should be able after I jump off the building with my table and my weight, I should go like this. It's like there's no problem lifting. In fact, the table is floating away from me, and I can just go in any direction. And that's what I would think would happen, which is in contradiction to what the speaker is saying, which is that when I jump off the building with my table and my lead weight, that it would still remain stuck to the table. I would not be able to lift it.
You must reckon that free fall is not a uniform movement. It is an accelerated movement. You are in acceleration when you are free falling. And that acceleration builds, together with the mass, a force that works in the contra direction, and it solves your problem. You can easily lift the heavy pound weight, 3,000-pound weight, from your table, because you are accelerating yourself. Your table is accelerating to the earth.
So who else do we have here? We have we have Alistair and Dionys. Now I'm kind of feeling like this discussion is kind of, we're kind of going in circles here. So, but I don't want to go in circles. I want someone to come up with a definite opinion about what's going on here. But I mean, getting back to the speaker's main point, though, is you're saying that what is gravity? You're saying something to the effect that gravity doesn't exist.
No, what I am trying to tell is, if there is no difference between free fall and when an object is resting on the surface of the earth, what does that mean? In the sense,
what does that mean?
In the sense, even during free fall, if you have to put effort to lift up the object, then there is no difference between, standing on the stationary on the earth's surface and lifting up an object, and lifting up an object inside an elevator which is in free fall. If there is no difference, that means only one thing: there is no such force as gravity. Because if gravity was there, then during free fall, you have to lift up any object effortlessly because its weight is 0 newtons. Mass is there, I agreed. We are not talking about mass, we are talking about weight. And weight is measured in a single pan weighing machine. whereas mass is measured by a scale which compares two different things. A single pan weighing machine shows the force of gravity acting on the object of certain mass. So in this, while falling when the elevator is falling, the single scale weighing machine is showing actually the force of gravity, and that is showing 0. Even as per calculation, weight becomes 0 because mass into acceleration is 0. So even by calculation, it is 0. So even then, if you have to apply weight, it means only one thing, no? That there's no such force.
I would actually come to the opposite. Even if I agree with everything you said, I would come to the opposite agreement.
One minute. At least, like, do you know this? This is what Newton actually told. We all only know what Newton told in his earlier days. But when he became little older and wiser, he said such a force can't exist. It is not at all possible. And he came out with 2 or 3 different theories which were not accepted by the mainstream scientists of that time. But he was very sure, and that is all available on the net. He says, no, such a force can't exist. Gravity is something else. It is due to the ether present in space. So what do you say? How do you answer Newton? Because he is the person who discovered all these gravity, universal laws of gravitation and everything. He himself is telling, when he's aged about 60 years, that no, such a force does not exist.
May I come in again?
Go ahead.
Yeah.
What's your comment?
I've bought the speaker's book. It's really interesting. But I do think that there is a problem about the concept of gravity. I think that if a man and a weight were both standing on independent scales in an accelerator in a lift that was falling at 32 feet per second, both scales would read no weight at all. And I think that doesn't mean that there's no gravity at that point. It means that all the equations come zero.
No, gravity is existing, but it is not acting on that 2 objects which are in the elevator at that point during free fall. That is what I am telling.
Well, if gravity is not acting on it, why is it falling?
No, see, okay. I'll ask you one thing.
Gravity, you can't.
No, let us think now. There's no gravity at all. You think object is heavy by itself. Let us just presume now. Let us forget. Let us think for a moment that there is no gravity. Objects are heavy by their nature itself. Okay. Heaviness is an inherent property of the object. Okay, that in that case, suppose I throw an object up, will it keep going? No, it will reach a certain height. It will reach a certain height depending on the force with I threw it. Then it will fall down. So
why will it fall down? What is just because it's got energy, just by itself, potential energy? Why won't it fall sideways?
No, that's what I'm telling. We are just imagining or presuming that there is no gravity, and weight is an inherent property of matter. So an object is heavy by itself. I'm just presuming. In that case, if I throw it up, it will decelerate as it goes up, and it will store potential energy in it. And
why is it slowing up? Why is it slowing up?
It is heavy by itself. No, sir. It is heavy by itself. You lift up. What is the intuition when you lift up? It is heavy.
Yeah, but
I'm just presuming. I'm just presuming. Let us forget that there is gravity. Let us think that weight is an inherent property of matter.
Okay.
I'm not telling. Just presume that way. So what will happen? The same thing will happen. If you throw up, it will slow down. It will fall down. The reverse. It will decelerate while ascending and accelerate while falling down.
In your book, you say that there is no up or down. So why does it fall down? Why doesn't it fall in any other direction if there's not gravity?
Up or down only in space. From the concept of space, there's no up or down. Otherwise, that is why, sir, on the Earth's surface, Earth is a ball, okay? It is a sphere. Yet all of us are sitting on a flat surface and looking on top. Why don't we feel inverted? Why don't we feel upside down? I mean, theoretically, if you see on the paper, on the book, you are standing, we are all standing in different directions. Yet each one of us feels that we are standing on top. So who's actually on top then? Everybody is on top. We are all on top. Earth may be a sphere, but it behaves like a flat surface. This is the concept I'm trying to think. It is a sphere, no doubt. But then we should feel inverted. One person at the equator should feel that he's standing at 90 degrees, and one person standing at the North Pole or South Pole should feel inverted. But nobody feels that way. Everybody, every one of us, from any part of the earth, we feel that we are on top.
But is it scientific to say what four people feel is actually physical and practical? I mean, it doesn't make it a flat surface, does it?
No. I'm not telling it is a flat surface. It behaves like a flat surface, I'm telling. And see, when we fly in a spacecraft, aeroplane also, we don't fall down anywhere or we don't fly upside down. As you will see on the animation, one animation I've shown, that is how we should have felt. When the aeroplane is going from the top to bottom, it should fall down at the equator side. Then at the South Pole, it should be flying inverted. And then again, it should climb up. But we don't feel that way. We feel always we are flying on a flat surface or a slightly curved surface. Why is that?
Well, I can't answer that, obviously, because that's not my subject. My question for you with your book is that I agree that weight is a property of matter, but just because it can have either potential or kinetic energy doesn't mean that in gaining that or expending that, it has to go in a particular direction. And yet you insist that the energy makes it go either slowing down when it goes up, or it has to fall down. But you deny that the direction in which it falls is affected by something outside of the energy it holds within itself.
No. I'm not very clear about that. Like, I did not get your question properly.
Okay, sorry. But you say if there was no gravity and you threw something up, you contend that object would gradually slow down and stop because of its own inherent weight. And you say that after that, it would then retrace its steps and fall downwards. And I'm saying is that I disagree with you in as much as you refuse to accept that there is another force acting upon it to make its behavior change during its distance of travel and direction of travel.
That is what I'm trying to. My point is that if in free fall and on the surface of a body nothing changes, then what is the effect of gravity? That is what I'm trying to find out. See, in free fall, even there you have to apply weight. Even on the surface of the earth, you have to apply weight. Then what is the thing? There should be some difference in free fall and when you are standing on the ground.
Let me ask you something. If there was no gravity, what would free fall be? How would free fall be created? What are the forces acting upon something such that it falls if it were not for the presence of a force like gravity?
Yeah, a force arises due to the heaviness of matter itself. Matter itself is heavy. Why do you need gravity to make it heavy? No, I will just ask a simple question.
But a planet
you are God. Suppose you think you are God. You are God. Now you have to make something heavy. Will you make a force and make it heavy, or will you make it that itself heavy? Then you don't need a force, no, that time. If the object itself is heavy, why do you need one mysterious force to make it heavy?
Right. Okay. I grant you that
another force is required to. Even mass they say is the Higgs field. The Higgs field gives mass to objects. They say so. Even that is a mysterious force. So why you need all that? Matter is heavy by itself. Finished. You don't need a Higgs field. You don't need gravity. You don't need anything.
I agree that mass has weight, or vice versa. So an object has its own intrinsic heaviness. But if there's no force acting against it anywhere, why should it move? its heaviness won't put it in any particular direction just because it's heavy. I mean, a rock out in space doesn't fall downwards, does it? It either travels because it has inertia or it's static relative to something else. Weight doesn't mean it moves.
No, movement, I'm not talking about movement. I'm just telling, see, my thing is, if free fall and standing on the Earth's surface is the same, where is the question of gravity? That is one day. There should be some difference, no? Free fall, you are falling along with the gravitational field. The floor of the elevator is equivalent to the floor of a celestial body where there is zero gravity. First, we must be very clear about that. The floor of an elevator which is in free fall, we are neglecting friction, everything. We are just assuming it is in perfect free fall. In the sense it is accelerating exactly at 32 feet per second downwards. So in that instance, the floor of the spacecraft is equivalent to the floor of a celestial body on which there is zero gravity. Is that correct?
But in your book, you say that every celestial body has an attraction because of its mass. I mean, how you're comparing a traveling lift with something that is incomparable. You can't have a celestial body without some kind of
no. I'm just
gravitational attraction.
No, if there is no gravity, then I'm telling you the floor of the spacecraft is a unique thing which is in free fall because it is zero gravity there. Gravity is there, but at that moment during acceleration, it is not acting on the objects resting on the floor of the spacecraft. That is my point.
Can I interrupt here?
So
have you heard of the vomit comet?
Yes.
Have you heard of the vomit comet?
You're asking me, yes.
So that is basically your falling elevator. Instead of having an elevator, you have an entire aircraft which is just decides to just fall at the same rate. It basically free fall. The entire aircraft goes into free fall, and you can see what happens to the occupants in that situation. So is that the same as your falling elevator? This airplane which just goes into free fall?
It should be. Should be the same.
Do you agree that that would be the same situation?
No. That is a temporary thing. This is a perfect free fall. Free fall continuously, it is falling at 32 meters per second. But that aeroplane does not go into a perfect free fall. It goes in an arc.
It's going in an arc, but still the contents are free falling.
See, even here, the scientists, I mean, the mainstream scientists confuse us. They say free fall around the Earth. How can you free fall in a horizontal direction?
Well, it's not. It's diving.
No. On the paper, the Earth looks small.
It travels in a parabola.
On the Earth paper looks small. I mean, the paper, the Earth looks small. But in reality, when we see, it is horizontal or slightly curved. So how can free fall occur in a horizontal direction?
It's not horizontal.
That's easy because you're going horizontal and then you're falling down. You see, this is a circular object. You're going horizontal, you're falling down, but the thing is that the curve keeps on falling further than you're falling. So
that's only on paper. Only on paper. But in reality, we are always flying parallel to the Earth. We're not falling towards the Earth. We're flying parallel to the Earth's surface.
Some of the satellites are hanging on a static position. Only the Earth is rotating underneath. And so that's not an arc, that's just a position. And the whole thing works indeed as a free fall elevator.
I mean, let's just take this from a logical perspective. So I give you my example of I jump off a building with my table and my 1,000-pound weight sitting on it, right? You understand that situation, right?
Yes.
Okay, so when I jump off, you're claiming that I still won't be able to lift the weight off the table.
Yes, definitely. You will not be able to lift up.
I will not be able to lift it up.
Yeah, you're talking about 1,000 pound object. Why 1,000? You think of a 1,000,000 pound object. Say it is very dense. You think of a 1,000,000 pound object. Can you lift it during free fall? It is not possible.
Yes, I would be able to lift even a 1,000,000-pound object off that table.
No,
Really, you're
impossible.
misunderstanding free fall. You must be.
I mean, the problem is that you won't even be able to tell that because my desk is going to start moving independently of say me, that I could push the whole desk away, I could push the weight away, I could push. I mean, you would in this free fall situation, you wouldn't even be able to tell which direction is up. And I could be flipped upside down, and you could throw me off the building upside down, and at that point, I still wouldn't be able to tell, what all that I would still be able. What I know is I would still be able to just easily lift that weight away from the desktop, right? Because even if I was flipped upside down, I don't think that's going to make any difference. The weight and the desk as I'm being thrown off the building would still be the weight. The weight would still be stuck on the desk initially, but as soon as you throw me off, I should be able to lift it up, move it to the side, right?
May I have a turn?
Yes, please go ahead.
All right. I want to use 3 objects. One that is 1 kilogram, one that equals my weight, we'll call it 100 kilograms, thereabouts, and one that is much heavier than me, say 1,000 kilograms. So I jump off of the building. I'm now in free fall with the 3 objects around me. I take the 1 kilogram and I try to throw it. It goes flying away from me. I could throw it upwards. It will go flying upwards. I then try to throw the object that's much denser and is the same mass as me. When I throw it, it's going to travel, and I'm going to travel the opposite direction equally. So if I throw the same object as me, half of the displacement is going to be the object, half the displacement is going to be me. If I then take the very heavy object and try and throw it, we'll still experience the same separation, only the object won't hardly move. I'll go flying the opposite direction. The mass of the object matters. If the weight that you're using on your desk, Franklin, is small, it's easier to impart relative motion to it. If it's very massive, then it's harder to impart a variation in motion. So the force necessary to give the object motion relative to you is different depending on the mass of the object.
And once again, this is the inertial mass argument, which I believe keeps on confusing everything. That's why when I did my example, I did it a binary example, that either I can lift this object off the desk or I can't, right? When gravity, full force of gravity is in fact in here. So I'm trying to reduce one of that. I'm eliminating that as a consideration here. That either I can lift this weight off my desk or I can't, right? Just to make it clear that we're talking about the force of gravity, not inertial resistance.
Right. But a couple of times I've heard people say, well, we need to consider reality. And the reality is that inertial force is a part of the situation and it's not removable. If we're talking about free fall, it's fact that the Earth is in constant free fall around the sun. Can I take my finger and easily move the Earth?
But we're not talking about the elimination of inertial mass here. That's why we don't want to discuss that, because it's not part of what the speaker is talking about. The speaker is saying that the full force of gravity remains in force even in free fall. That's what the speaker is saying. That's a big difference.
Yeah, I would call that a false statement, that the full force of gravity is still in existence in free fall. Free fall is, by definition, removing the impact of the force of gravity. It's balancing it out. It's not eliminating it. It's balancing it with change in motion.
Yes, but the speaker is definitely saying that, you know, if I were to have like a 2,000-pound weight sitting on my floor here,
Yes.
that even if my whole house went into free fall, I would not be able to lift that thing up. That's what the speaker is saying.
Right.
And I think I would claim that what's wrong with the speaker is that is actually not correct. That if that were the actual situation, the actual practical situation, when my house went into free fall, I would be able to go just like that, very easily.
Yeah. I would agree more with your expectations than to imagine that it would still be stuck and you wouldn't be able to move it. I think you would be able to move it. Just the ease with which you would be able to move it is dependent on its mass.
Yeah, there is still some force required. Not
yes,
zero force.
You would be able to move it, yes.
You would not have to fight against the force of gravity to do that.
Correct, because the force of gravity has been balanced out, eliminated by change in motion.
Yes. Okay. So just to make it clear what we're talking about here and what the differences are, because the speaker has some very, very, it's a radical idea that even in free fall, that you would have to overcome the full force of gravity, and that would not be able to lift that thing up.
Right. You wouldn't have to overcome the force of gravity because your change in motion is an acceleration. Therefore, the force of gravity is already eliminated by your constantly changing rate of motion.
Now, the speaker, he did claim to have an experiment that he performed. So why don't you go ahead and explain that experiment where you actually did this experiment where you had a spring and it was able to attract an object if it had less force. Let's see here. Let's go back to that. Let's see here. Where is that? I'm trying to cue it up here. So let's go. Let's take another look at that. So this is a contradictory experiment. This is showing that the object maintained its weight throughout the free fall, and which would contradict, what say NASA would say. So I mean, I suppose the argument is that none of those situations actually represent a legitimate elevator free fall. So the Vomit Comet doesn't do that. The orbiting spacecraft don't do that. So let's take a look at that video again here. So I got to get my share menu up.
I don't see our guest speaker in our list of participants currently.
And not a property endowed by gravity. Some videos posted by reputed space agencies show similar experiments where an object hanging from a tension spring immediately appears to rise up when the contraption is dropped, giving the impression that the object's weight has really become zero. However, what is really...
Let me see if I can re-cue this video. It's like it's got the wrong aspect ratio. My computer is just a little bit slow here. But let's see here. So where is this experiment here? Okay.
Which on in 1 or 2 seconds after free fall has begun. If the weight of the object really becomes zero, then the electromagnet's attraction will pull up the object, which will then attach itself to it. However, if the object retains its weight, then it will continue to remain resting on the weighing scale even after free fall is completed. In the experiments I conducted, the object was always resting on the weighing scale during and after free fall, proving beyond doubt that a gravitational force does not exist and that weight is an inherent property of matter and not a property endowed by gravity.
Okay, so that's the speaker's experiment there. All right, so what do people think of that experiment? That when he conducted that experiment, that the weight did not attach to the electromagnet. It stayed on the platform, on the weighing platform. So what do people think of that experiment?
For me, I don't think there's enough information to make a judgment, and we don't know whether it was truly in free fall, how long it was in free fall, what were the relative weights and attractive measures of the magnet. I think we need to know more before we can judge it as a useful experiment.
Well, what if we just, assume that everything the speaker said was correct, which was that he's got this experiment that he did, that he thought he's got an electromagnet that's strong enough to pull the weight away from the scale if it's less than its full gravitational weight, but not strong enough to pull it away if the full force of gravity is present. And he observed that at the end of the experiment, the weight is not attached to the electromagnetic. So, Mohana, we have you back here. So why don't you explain a little bit more about that experiment? So I think you are cutting out there a little bit, but I just showed the video of your experiment that you used to prove that the force of gravity is still present even in the case of free fall. Yeah, I think that we're having some communications problems over there. He is in India. Because right now the video just froze up. So he may be having some internet connectivity problems. But my questions would be, is like, if the only thing he's doing is observing the position of the weight before and after the experiment, then how do we know that the weight didn't just fall back down from the magnet after the experiment was done? I would expect that would be the case, that as soon as that whole object stops moving, that the force of gravity would then come back into play and it would cause the object to drop back down to the bottom. I would never expect to see the object to remain stuck up to the top because it just doesn't have enough force to keep it there, right? So how could you observe it staying there, confirming the negative hypothesis?
Also, wasn't the experiment meant to prove that there wasn't gravity rather than that there was?
No, the purpose of the experiment was to prove that even in free fall, the object would remain attached to the scale with a force.
Right.
That's what they're trying to prove. So there's two hypotheses. It's either that things retain their weight property even in free fall, in which case the weight would remain on the scale, or that if the object really, lost its gravitational effect, then it would be attracted up to the weak magnet, which can lift up something less than 250 kilograms. It can lift up 150 kilograms, but it cannot lift up 250 kilograms. So what I'm imagining is that, well, it could have attracted that object up to the magnet, but as soon as the experiment ended, then it would, of course, fall back down. right? So what's the evidence that it stayed on the weighing scale the whole time? That would be my question.
Mine too.
So I would generally suspect that that it in fact did go up and attach to the electromagnet, and it just fell back down at the end of the experiment. So because if that experiment were, as the speaker says, then that would be evidence that there is still some force that remains even during the free fall situation that keeps things pointing in the downward direction, or at least on top of something else, right?
I mean, this is just diagrammatic, isn't it? I mean, if it should have been done with a camera traveling alongside, just so we could see what happened while it was in free fall.
Yeah, I think that would have been a much more convincing presentation if there was actually a camera along board, which now we can actually do because of small camera is about this big. I've got one on my little drone that's about this big. You could easily have stuck that inside such an experimental setup to videotape the entire thing as it happens.
Yes, because at the moment, really, it's just a theoretical experiment, isn't it?
No, I think he actually did this experiment.
Well, yes, in his book he says well, it's not totally clear, to be honest.
So let's see here. Mohano, do we still have you? Because your video faded out, and I see you're still on the conference, but I don't hear you talking. Can you say something? Are you still on the conference? Are you still there, Mohano? No, I don't think so. Although, while we're waiting for him to come back, so I did find some interesting footage on, say, the Vomit Comet. And let's just have a look at that and see what really happens and what people... Are you back?
Yeah, yeah.
Okay, yeah, we kind of lost you there. I think your internet connection was slowing down. So, but I was going to show some fun video on what happens when you go into free fall in the Vomit Comet, just for fun here. So let's see here. So it's actually kind of hard to find a clean video of this. But here's some people. This is what happens. All right. So actually, those people seem to be falling up. Those people seem to be like going towards the ceiling. And it doesn't last very long. I mean, if that was the actual arc there, that was probably less than 15 seconds. But that is what they would point out and say, this is what happens during free fall. That's what would happen in your elevator. That everybody would just suddenly leave the floor, and they could push each other around easily. There's really, in that situation, no way to define actually picking up something. Just you can't even define that there's a floor that you're picking up against once that free fall situation kicks in. So, but what did you think of that video?
No, that video in first 15 seconds they will feel weightless, then they will feel 4 times the gravity afterwards. It is not a parabolic flight. It creates a free fall like situation, that is all, because they will experience weightlessness for 10-15 seconds, and after that no they will experience gravity, huge bump. You can see the video or you can study it, no, that it is not perfect free fall. Perfect free fall is when you're falling vertically towards the center of Earth's center of mass at the rate of 32 feet per second. That is perfect free fall. Nobody floats in that situation. No, this experiment can be tried practically. That's what I was trying to tell. There are skydivers in US. We can take their help and conduct a practical experiment itself. Because mere discussion will take us nowhere. We can conduct a practical experiment using those people, skydivers.
Yeah, so I was showing your video of your experiment. So did you actually conduct that experiment where you had the electromagnet? And so you actually conducted that experiment?
Yeah, I conducted first with a permanent magnet. Then it was always going up. Then I was wondering why. Then I knew like it is acting like a spring, because the magnet will be exerting a force on the object. So as soon as it falls, the free fall begins, it will get attracted. So then I put on an electromagnet, and then I saw that it was never getting attracted. It was always resting. Only thing, the full contraption broke down. I didn't have a video of that. One I posted on the YouTube, which I will try to link it, post it on your website.
Well, in our discussions here, I don't know if you heard it. So we would have liked to have seen that experiment done with a video camera on the object at the whole time, since the doubt was that the thing that you have to eliminate is the possibility that during the free fall that the weight did actually go up and become attached, but at the end of the experiment it just fell back down, so that when you opened up the experiment you say, it's not attached to the electromagnet, it's on the floor.
No, this is such a simple experiment. Even anybody can do it. Even you all can do it there. It is not at all expensive or anything. You can try it out also, so that firsthand you will come to know what is happening.
How did you? You say it's easy to do. If I wanted to do it, how did you create the free fall? The environment.
No, I went on to a very tall building and dropped it. Of course, that is not perfect free fall because air is in. But more than 90% is a pakka free fall. I went to a very tall building and dropped it from there.
And so it didn't break. What happened when it stopped?
Finally broke. First I tried strings to it and I tried all that. But ultimately, after 4 or 5 attempts, once my result, I could get my result, then the string snapped and it broke into pieces.
But how do you know what happened inside the box as it fell if you couldn't accompany it or video it?
No, that broke after 4 or 5 attempts. In the first, second, third attempt, I was able to know that.
That didn't answer the question.
Yeah, I think it's a really difficult thing to do, to create free fall over a distance where some object can actually achieve 32 feet per second. Now, it has to fall quite a long way before that perfect free fall situation is created, and then we have to believe that what happened in the box is what you say, even though you had to pick up a lot of broken pieces at the end of it. I'm afraid I'm not convinced by the experiment at all.
No, you can conduct it yourself, no? Or we can use skydivers. We can that will be the best way. While skydiving, we make a platform which has a rocket-like thing at the bottom to decrease air resistance. And from 10 to 15,000 feet, he will have his parachute on, everything, and on the platform he will be standing along with the object, which is about 10 or 15 pounds or 20 pounds, whatever. So once the free fall starts, he can lift up the object. Practically he will know whether it is heavy, whether it is light, whether it is floating. Then once he conducts the experiment, he just opens his parachute and he will land safely.
So is that what you did?
No, I haven't done that. Because here it is not allowed. Here they are very strict. This can be done in the US. So, no, it is very important. No, this is see the experiment to check Einstein's theories. They are spending billions of dollars. Why not we spend some $1,200 and conduct this experiment with the skydivers?
Well, from what height did you drop your box?
Mine is about 120 feet. That is all.
And it
about 100
reached,
to 120 feet.
It reached 32 feet per second in 100 feet.
And I could not go higher than that.
No, I know, but my question is, did it reach perfect free fall in such a small height?
No,
I mean,
perfectly.
It would hit the ground. It would hit the ground before it reached free fall.
No, I could be fully, because of air resistance. It will not achieve a perfect free fall.
If it doesn't achieve free fall, what's the point of the experiment? I don't.
Not perfect, but it is 90% free fall. Then the weight should have decreased by at least 90%, if not 100. At least 90% the weight should have decreased.
Yes, but then how did you know what happened in the box whilst it was falling?
I was taking a thing from external camera. I was shooting it. Another person was shooting the film.
What, another person was traveling down with it?
No. He was standing at a little distance and trying to take snaps, video. Well,
so the box had glass sides, did it, or plastic see-through, transparent?
Yeah, glass. Not glass, acrylic.
I wish you had just one or two pictures of the real thing rather than just.
I will post it. I will post it. It is on YouTube. Only thing, the link is different. I will give that link. I will send it to Mr. Franklin.
Okay, great.
So he can. Yeah.
Okay, so the experiment did have see-through sides, so we could actually see the object inside. So yes. Visually, you could observe that the object remained on the bottom of the falling object, is what you're saying.
Yeah.
But then again, that would kind of beg the question that if you didn't achieve complete free fall, then we would expect that, the object would remain at the bottom of the object at all times. But I suppose you did have the electromagnet that would have pulled it up, I guess, right? So you didn't observe the object being pulled up by the electromagnet.
Though you did. When I used the permanent magnet, that time it was pulling up every time. But then I knew it is wrong. We should not use permanent magnet. Because that time, every time it used to go up. So I was thought really gravity is there. But when I changed to electromagnet, then it was not pulling up.
So you were able to switch on an electromagnet whilst it was falling, and presumably it's quite
I put a timer inside.
So it's traveling with a battery and a radio switch.
Yeah. No radio switch now.
I mean, I think you could just keep it turned on. You just turn it on at the beginning of the experiment. It doesn't have enough force to pull the weight up. And your audio is breaking up there.
From my point of view, I think the Vomit Comet is a very good match to weightlessness created through traveling 2 feet per second, where it is a genuine free fall. And I think that would probably be the place to carry out these experiments. I mean, it's so critical, the results from this. I think experiments have to be approached meticulously.
Well, but he would Mohono has a point that is not the same as completely vertical free fall. That there is a significant arc going on there. Now, even if there is an arc going on there, I mean, what would be the effect of that? I don't know that would have any particular effect on this type of experiment. That it's an arc.
Well, the vomit comet actually accelerates downwards faster than freefall, which is why they tend to go to the roof. And of course, if you just looked at one of the other ones as the weight, you can quite obviously see that he could move a weight about quite easily whilst in freefall.
Yeah, while you're in the vomit comet, if you had an experiment, you wouldn't even know which way to orient the experiment so that's pointing towards the center of mass to the Earth. It would be the problem because you really don't have any clues as to what that is.
That's a really good point.
I mean, how could you keep your experiment, if you're in the vomit comet, pointed towards the Earth to prove that some object inside of it is still being attracted in that direction? I mean, that's the crux here, is that the object will still be with some force going towards the center of mass of the Earth, even in the vomit comet. But it seemed quite clear that when you're free falling, you don't have those clues. Or do you? I mean, this is why I like experiments. I mean, I really admire people who go out and do their own experiments and come up with their own results. Because if you are trying to prove something which is fairly unique, which is an actual elevator fall, because like I said, mainstream would point out, people in space orbits obviously don't have any problems moving stuff around. People in the vomit comet can push their 100-pound partners. Even skydivers, when they're skydiving straight down, have no problems when they form up with their formations, and they can easily fling their partners away as if they weighed nothing. Or they could perform like push-ups, for example, and against another person as the floor, and it would find that you can do that without any effort at all. You could do 1,000 push-ups, one skydiver on top of the other. I suppose that would be a fairly easy way of doing it. Would you agree that if we just had a bunch of skydivers, like 3 of them made the floor, and the other person is going to do push-ups, that you would say that that person doing push-ups is going to have to do the same force as he would on the Earth? What would you think that would happen in that situation? Did you hear my question? Skydiver experiment. Did you hear my question, Mohono?
No, I didn't. It was couldn't get connection problem. What is started?
Yeah, connection problems. Must be the man interfering. We're getting too close to the truth, right? Yeah, I always find this funny that whenever we're trying to say something important, the internet connection cuts out. It must be the man. But, okay, can you hear me now?
Yeah, no, I can hear you.
Okay, so this is the experiment I'm suggesting. So you get 4 skydivers, okay? So the first 3, they go out and they make a floor themselves, right? So they define, and they're falling straight down. And then the 4th one, he goes and he does like push-ups on those 4 guys. So in that situation, would the push-ups be as difficult as they would on the Earth? Or would it be like, oh yeah, I can do push-ups like this all day long because there's nothing? What would you say would be the
It would
result
be
of that
as
experiment?
difficult as it would be.
Oh dear.
So,
If we've lost him, I'd say you do one push up and he
on
wouldn't
the
come
earth.
down again.
so Mohanel says that it would be just as difficult as it would be on the Earth, I believe, is what he said. But I would think that he should be able to do one-handed push-ups. In fact, he should be able to push-ups with his pinky. It should be.
Theoretically, why don't we do practical experiment? That's what I'm
No, I
telling.
think you should find some skydivers to do that exact experiment, because that doesn't require any equipment, any fancy. All that requires is four guys and a guy with a camera, right? Or, I'm sure you might be able to convince someone to do that.
No, I do the experiment. What I'm suggesting, we make an inverted rocket-like capsule. The skydiver stands inside that. There's a heavy object also. It is taken up in an helicopter and dropped from 15,000 feet high. That would be a perfect experiment, no? Instead of doing all sorts of gymnasium and everything. He will lift up directly.
I was just trying to find an experiment that you could do that didn't require any extra equipment.
No, it is required, because experiments are very, very important, because it is a fundamental fact of physics that we are trying to find out. So it is important. We spend some money and we do it in a proper way, because that ultimately it is experiments which will give us results. No discussion will give us results. Experiment only will give us the proper result.
So all we have to do is take like a telephone booth with a 300-pound weight in it and drop that from 15,000 feet and ask the skydiver to lift up the weight and see, is it still stuck to the floor? I mean, we arrange it so that the whole elevator drops straight down in accordance with gravity, and see whether he still has a problem lifting that thing up.
Yes, it is possible. They are doing so many dangerous stunts. This will be very easy for them.
Yeah, it'd be easy for skydivers. But like I said, it would be easier, even easier, if you could come up with an experiment that doesn't require any extra setup. Or since I'm pretty sure, based on what I observed with skydivers, that if they were doing push-ups on each other, that it would take no force to do the push-ups. In fact, the action of trying to do the push-ups would just merely push the other skydiver away, and you would actually have to have your hands glued to the other skydiver so that when you went down for your push-up, you wouldn't just immediately just disconnect from the skydiver, because there would be nothing keeping you connected to the other skydiver.
Be careful with skydivers, because due to the air resistance, they don't go into a free fall. They are going down much slower than with a free fall.
Yeah, but I think for purposes of determining whether the weight is still there, at least 98% of the effect should be eliminated. But I'm pretty sure if they did that experiment, they would find that it takes no effort at all. But then again, it's like I can't do that experiment. I'm only presuming what I think would happen. Not that I have done that experiment or anything like that, but that's what the mainstream would say. I would say, at least.
When skydivers fall, they reach a maximum speed. They don't keep it. There's no continuous acceleration.
Yes, that's right. They reach terminal velocity. At which point, theoretically, after they reach terminal velocity, then the full force of gravity should once again be in effect. So maybe that wouldn't be the best way to do it. Because probably if they reach terminal velocity, and maybe this is what happened in your experiment, I don't know. Once you reach terminal velocity, then you're no longer accelerating, and the force of gravity can once again drop a weight to the bottom of any free-falling container. That is an interesting possibility. That's hard to eliminate
No,
here.
no, I agree. My experiment is not very because the drop height is very less. Only we'll get proper results when the drop height is about 10,000 feet, at least 10 to 15,000 feet. From that, if you conduct experiment, that will give us the best result. And I think it is worth it if we do it. Because discussion will never take us anywhere. There will always be a difference of opinion. Experiment is the one which will prove one way or the other what is true.
Yep, that's true.
See, even
So,
Galileo, he rolled balls and all that, and he found out that all objects accelerate at the same rate. So, experiment is the most necessity thing to arrive at the truth. Discussion will never take us anywhere because each of us have our own, but experiment result will always be the same. It will not show different results.
but I just want to make sure. So let's suppose they do the experiment exactly the way you say, and indeed the person is able to lift the weight easily. Then would you be willing to concede?
Definitely.
All right. See, that's
If
true
he is able
science.
to lift it, then there is gravity.
All right, because some people they wouldn't even if I mean basically their theories are not falsifiable, but in science I think what you say is absolutely true, and I think we're at the top of the hour, so I think I'll begin my little bit of summary, but I think it's absolutely true that talk is cheap. Talk is cheap. If you have an experiment, I mean, the way experiments go is that, the results should unequivocally be explained by one hypothesis and deny another. So some experiments have been done, and other experiments. I mean, we've heard some descriptions of the speaker's experiment where, he had apparently has a clear container, dropped it off the top of this building he could find, and saw that the object remained attached to the bottom even though it was attracted by something that should have theoretically been able to lift it off. And that he got different results with permanent magnets. I mean, that's kind of a control experiment just to show that it is possible to observe the opposite result, which is that it attracts up to the top and it stays there. So I would say that, that's good experimental setup to make sure you have controls to show that the experiment can go both ways. But that ultimately the results of those experiments should guide you as to what the truth is, and you would be willing to accept the truth even if it doesn't agree with your original hypothesis. So, and I think that is real science. That is what real science is about, and how we should be going about it. But so today we had discussed this theory that objects basically retain their property of weight even in a supposed free fall situation. I think we clarified that what we're talking about here is not the inertial force required to move an object if it were no gravity force. We all know that the inertial weight exists, but that force is very, very much smaller compared to what we would consider the gravitational force. So that's what the speaker has proposed, that if we do this experiment, and he would be happy with skydivers at 10,000 feet. So if there are any skydivers watching this video, we want you to volunteer for this experiment and prove this one way or the other.
We'll pay them.
Franklin, it is a false experiment. There are so much errors in it, I wouldn't suggest to do it.
Well, it might make Mohan happy, or I mean, if it comes out negative, then it's like, okay, then I have to go on and then say, never mind. Or maybe it's confirmed, and it's like, well, that's totally opposite of what the mainstream thinks it should be. So I think it'd be a reasonable experiment. So that's that. But I think that will do it for this discussion of how gravity works. And so next week we can do this again on your ether theory.
Yes, yes.
All right. So he's got one more video. So like I said, everyone go and watch his video beforehand. It's very interesting. And but that will do it for this week's episode of the Science Chat. So thank you for all participating.